Hi, I'm Elijah Smith. My master's project is exploring seasonal trends and episodic weather in the Muskegon Lake ecosystem. For the last 10 years, the AWRI at Grand Valley has been collecting buoy sensor data from Muskegon Lake to study the regional ecosystem. They had a few project ideas that could benefit from computer science assistance. First, general data analysis and visualization of trends, seasonally and over multiple years. Specifically, the interplay between water temperature, dissolved oxygen, and algal blooms was all of high importance to them. Second, exploring the time-delayed effects of meteorological events, such as storm mixing and bottom nutrients, and this impact on subsequent algal blooms. Third, creating a live dashboard for weather and water quality to be displayed on the AWRI website. The data itself was almost a decade's worth of time series data in 15-minute intervals. The buoy has a large number of sensors, giving more than 30 raw data points at every interval. All said, we had a limited subset to tackle the problems at hand. Specifically, we focused on the temperature readings across all depths to measure the stratification of the lake, the bottom dissolved oxygen readings to measure hypoxia, wind speed and direction to label episodic storm events, and chlorophyll and phycocyanin to track algal blooms. Here's a picture for scope. Over the course of the project, we were able to provide analysis and visualizations to AWRI covering trends, and we were able to make significant progress on the other two problem areas. Before getting into the details, let's take a step back and review some lake biology. Here I have a 5-step sequence of what an algal bloom might look like in Muskegon Lake. First, stratified water layers form during the warm summer months. Second, when the stratification happens, the lake doesn't mix easily, and decomposition at the bottom takes up all available dissolved oxygen. This leads to hypoxia. Next, an episodic wind event occurs, mixing the stratified layers. Finally, calm periods with little wind allow algae to congregate. If the calm period continues, a period of high algae called an algal bloom may occur. Harmful algal blooms contain toxins that harm people and the ecosystem. So that's a high-level description of how some of these processes and metrics relate to each other. For the project, I started by cleaning the data and visualizing the relationships in Tableau to make sure the data agreed with the science. Here we have a period from the last week of August 2014 to the first week of September 2014. In the top chart, we have wind speed over time, and we can see periods of high wind events here with these spikes. In the second chart, we have water temperature at various depths over time. Each line here represents a different depth on the buoy sensor. So at the beginning, we can see the lake is relatively stratified. Then there are a few mixing events that occur here when the lines come together at 70 degrees. In the bottom chart, we have bottom dissolved oxygen over time. We can see these spikes also coincide with the high wind events. Our next step, knowing our data is validated, is to quantify these metrics. For example, it is easy to visually see the stratified layers and mixing events in the temperature depth readings. But to support future modeling and measure the significance of each event, we need a data-driven way to evaluate or compress these temperature depth readings. For temperature at depth, we wanted a snapshot of how stratified the lake is. I came up with the idea to calculate the difference between the top and bottom layers as a new metric to convey this, and wrote a Java program to calculate this data. Taking this one step further, I knew we needed some way to determine how the stratification metric is changing, so I decided to use the gradient of this temperature difference reading to calculate the rate of change for the mixing events. This gave us insight into quick mixing events as opposed to a gradual mix. Finally, by applying a threshold filter, we can come up with a subset of significant events. All of this was done in Java. This graph marks each of these significant events with vertical red bands. You can see these coincide with declines in the temp diff metric and with low values in the temp diff gradient. For wind speed, an adjusted measure was explored to combine the direction and strength of wind. Due to the physics of lake mixing, wind that blows across the longest length of the lake is most effective at initiating a mix. So this adjusted wind speed was calculated using a sine function transposed to 36 degrees, which is the fetch of Muskegon Lake. Finally, chlorophyll and phycocyanin are two metrics used to measure algae concentration. All algae contains an amount of chlorophyll, whereas only harmful algal blooms will contain phycocyanin. To label and color significant algal blooms, we use Tableau to calculate standard deviations and apply them to these formulas. Putting it together, we combined all these metrics into a single seasonal chart for ease of use. Many other visualizations were created to explore daily and interannual averages. To further our understanding of the impact of episodic weather events, we wanted to find out the time delay between correlation. For example, we knew that periods of high wind correlate with increased dissolved oxygen, but we did not know how much of a delay there is between events. A statistical function called the cross-correlation function, or CCF, calculates this by shifting two datasets. We ran this CCF function in R, which revealed a delay of about 4 hours between high wind and declining temperature diffs, and a delay of 13 hours between high wind and increased dissolved oxygen levels. Intuitively, this makes sense, as the cyclone that churns the lake does not occur immediately, and the dissolved oxygen diffusion takes longer than water mixing. As a final part to this project, I created an animated dashboard snapshot view of Muskegon Lake. The long-term goal will be to expand this into something that can be used for the live buoy data instead of just the historical data. This dashboard was created using JavaScript and D3. Finally, wanted to acknowledge and call out everyone on the project team that's given help. Anthony Weinke from AWRI, Dr. Badana from AWRI, Professor Leidig and Professor Wolf, and Michaela Berg. Thanks to all.